Welcome to the University of Chicago Apprentice program. So this is the first lecture, and I want to start with some topics in combinatorics. So the first lecture will be about bijections and permutations. Okay, so let's start a little bit philosophical. So consider the following statement: 4 equals to 4. Of course, it seems that's a complete triviality, but when you start to think what it actually means, things become a little more complicated. So what is 4? So 4 is an abstraction for any set with 4 elements. So each number 4 represents our idea of 4 elements of various sort, and so it can happen that this 4 stands for one set of 4 elements. For instance, lion, cat, tiger, and cheetah. And this set of 4 may stand for a completely different set of elements. For instance, burger and pizza, pasta, and borscht. So in which sense these two sets are the same? So of course they are absolutely not the same, but what this identity means, or equality means, is that there is a way we can identify elements in one set with elements in the other. For instance, we can associate burger to a tiger, pizza to a cheetah, pasta to a cat, and borscht to a lion. And of course, this identification is completely random. So the only important thing is that there is a certain way to identify elements here, so that basically for each element here we have exactly one element in the other set. For each element in the second set we have exactly one element here. But what is interesting about it is that such identification is not unique, and there is no natural one actually. People can argue what is the better way to what is the best way to identify these two sets. So in a sense 4 equals to 4, not in one way but in many different ways, and the number of ways to identify these two sets is actually equal to 4 factorial, being 24, and so there are 24 different ways in which 4 equals to 4. So permutations are exactly this kind of ways to identify the set with itself, and bijections are more generally ways to identify different sets. So I expect that most of you are familiar with bijections, and maybe some of you have heard about permutations, but let me start with just a definition of a bijection, so that everyone will be familiar with the first couple of minutes of the story. So definition. So let's take a pair of sets, and f is a certain map between sets from A to B. It's a function. So I will use the word function and map interchangeably. I don't know what is more familiar to you, but both mean the same. And then, so there are 3 important definitions. So f is injective. If for any 2 elements a1, a2 in A, if f of a1 equals to f of a2, then a1 equals to a2. And f is surjective if for every element b in B, there exists a certain element a in A such that f of a equals to b. So let me draw this kind of familiar picture. So you have one set and the other, and we have a couple of elements. So the fact that we have a function means that for every element in A, we know where it goes in B. So we need to prescribe exactly where to go. And injective means such picture is not allowed because 2 elements cannot go to the same one. That's property 1. And the second one, surjective, means that everyone is covered and the fact that there is something which does not come from anywhere, that means this map is neither surjective nor injective. So neither surjective or injective. Okay, so what is bijective? So F is bijective, or a bijection, if it is surjective and injective simultaneously. So both properties together mean that basically distinct elements go to distinct elements, and moreover, to each element here there exists exactly one element here which corresponds to it. So you can, in a sense, reverse the arrows and say that this is a one-to-one correspondence. For every element here you have exactly one here, and vice versa. So basically you can think of these two sets as kind of the same. You can identify them in a certain way, but they are the same in the same sense as this one is the same as this one. Okay, so this is a definition of a bijection. And then, so if you have, so we have a particularly nice set 1 up to n, just n numbers. And if A is, let me call the set n, as people sometimes do. So if there exists a bijection between A and n, we say that cardinality of A equals to n, or simply A has n elements. So this is this classical idea of the sets have elements. 4 elements here, 4 elements there. There is a bijection between both of the sets with the set 1, 2, 3, 4. Okay, so probably this is familiar to everyone. Let me now go to maybe more tricky idea of a permutation. Okay, before going to permutations, maybe another example. So another example. So let's consider the following interesting situation. So consider a set n, and this will be A. And B will be a set of even numbers. So elements to K, where K is inside n. These are just even numbers. So clearly there exists a bijection. So there exists a bijection from A to B, F, and F of n, maybe F of K equals to K, is a bijection. But that's true despite the fact that clearly B is a subset of n. So we have to say that, so we say when there is a bijection between two sets, we say that cardinality of A equals to cardinality of B. And it's true despite the fact that B seems to be smaller than A, because B consists of even numbers, so it looks like it's twice smaller. But from the point of view of this kind of size of sets, that's not true actually. They are in a bijection, so the number of elements there is the same. So sets in bijection with n are called countable, and there is a beautiful symbol. So their cardinality is denoted by this letter Aleph 0. So there are lots of examples of interesting sets which look as if they are bigger than the set of positive integers, but actually they're in bijection with it. For instance, it's a famous and relatively easy fact that the set of rational numbers is countable. And for instance, the set of reals is not. So I'm absolutely not going to deeper in the theory of cardinalities of infinite sets, I just wanted to say that we will talk about combinatorics in the beginning, which is basically the science about counting finite sets mostly. But there are lots of interesting facts about infinite cardinalities, and very few of them we will touch. Okay, so let's go back to finite sets. So another little definition is that, so let's suppose that cardinality of A is equal to n. Maybe let me switch notation. I will denote this set by, so let me denote by S. So S will be the set 1 to n. I will use this notation a lot. And so a bijection sigma from S to S is called a permutation. So it's very important that it's not just a bijection between two sets with an element, it's a map from the set to itself. So you know, kind of, you have the same labeling of element in the source and the target of this map. So let's go through some examples, and also I will explain certain notation. So let's, for instance, take n equal to 1. So examples. Let's take n equal to 1, and then there is not much we can do. So basically there is this just set with one element and set with one element, sorry. So we want to map it to itself, and there is just one way to do it, and that's 1. So the number of permutations, so there exists a unique permutation of the set, which just doesn't do anything from S to S. So with n equal to 2, that's more interesting, because now we have two elements, 1, 2, and we can either send 1 to 1, 2 to 2, so with these arrows I just explain which goes where, or I can send 1 to 2 and 2 to 1. So there are two different bijections between the set to itself. And what is the notation for it? So notation is just I take this sigma and I write it down, and I write down this kind of a little matrix where in the first row I have all the numbers 1 to n, and in the second I just say where they go. So for instance, for this permutation, let me maybe use some other color. So for this one, that's 1 goes to 1, 2 goes to 2. For this one, it is 1 goes to 2, 2 goes to 1. For this one, it's 1 goes to 1. But I can easily come up with a much more complicated example. So for instance, I can take 1, 2, 3, 4 goes to 3, 4, 1, 2, and this will be a permutation which takes 1, 2, 3, 4 and sends 1 goes to 3, 3 goes to 1, 2 goes to 4, and 4 goes to 2. So that is what it does. Okay, and this is a permutation of a set with 4 elements. So that's an example for n equal to 4. Okay, so the next question is how many permutations are there, and what interesting stuff can I say about them? Okay, so for that, let's consider the case n equal to 3 before going further. So the notation is that I denote by Sn is a set of permutations of the set S equal 1 to n. So for n equal to 3, let's just write down all elements in S3. So we have now 3 elements and we want to permute them. So again, permutations are very easy to visualize. You just take 3 elements of a set, 3 elephants for instance, and then the question is how many ways are there to permute them with each other, like move them around so that we have the same 3 elephants going in some other order. So for S3, there are 6 different ways. So, and there are a couple of ways to draw them. I will just draw one after another 3 ways to visualize permutations. So the first one is this. So I take 1, 2, 3 goes to 1, 2, 3, and that means that every element out of 3 stands where it is. So the second way to draw it, you can just say, okay, 1 goes to 1, 2 goes to 2, 3 goes to 3 by these little arrows. And finally, you can draw it as 1, 2, 3, and just say with an arrow where everything goes. So these are 3 different ways to draw permutations, and they are useful for different purposes. So another one is where we exchange 1 and 2. And this is it. 1, 2, 2, 1, 3 goes to 3. And we have 1 and 2 are exchanged. 3 is fixed. So then there are 2 other permutations which look roughly the same. So they exchange 2 other elements. For instance, I can exchange 3 and 1 and leave 2, or I can exchange 2 and 3 and leave 1. So that will look like 1, 2, 3 goes to 1, 2, 3, and 1 goes to 3, 2 goes to 2, 3 goes to 1. Here I have 1, 2, 3, 1, 2, 3, 2 goes to 3, 3 goes to 2, 1 goes to 1. So 1, 2, 3, 2 is fixed, 1 and 3 are exchanged, and 1, 2, 3, 2 and 3 are exchanged, 1 is fixed. So finally, there are 2 remaining permutations which look sort of different, because here all 3 elements are fixed, 1 element is fixed, all 3 elements move around. So 1, 2, 3, 1 goes to 2, 2 goes to 3, 3 goes to 1, 1, 2, 3, 1 goes to 3, 3 goes to 1, 2 goes to 1, 3 goes to 2. Okay, so let's draw them. 1, 2, 3, 1, 2, 3, 1 goes to 2, 2 goes to 3, 3 goes to 1, 1, 2, 3, 1, 2, 3, 1 goes to 3, 2 goes to 1, 3 goes to 2. And here it's what's called a cycle. I will define cycles in a moment. And here 1 goes to 3, 3 goes to 2, 2 goes to 1. And now you can see just all ways to permute 3 objects between each other. So in particular, cardinality of S3 is 6. So that's kind of interesting picture already, because you can start thinking, okay, so there are tons of interesting stuff here. So some of permutations have fixed points, elements which don't move. And you can start asking how many permutations are there in Sn fixing 1 point, fixing several points. There are these cycles, sequences of elements which kind of exchange in a cyclic pattern. 1, 2, 3, 3 permutations have the cycle of length 2. And these 2 have cycle of length 3. So when you see all of that, you start to understand that maybe this structure of the set of permutations is rich. And indeed, we will talk a little bit about that, and you will learn much more in Groups 1, Algebra 1 course when you take it. So maybe before that, let me just say that so again, these are just all ways to explain like in which way 3 equals to 3. So this simple identity has this all complicated combinatorics behind it. So before I move on, I want to give you 2 little exercises. So exercises are as follows. So first one is draw all permutations in S4. And you can draw some in this way, some in this way, some in this way. And the second exercise is that proves that the cardinality of the set of permutations, the number of such permutations, is n factorial. So there are n factorial ways to permute. So n factorial is of course n minus 1 times 1, and this is a number of ways to permute elements with each other. So a convention is that 0 factorial is equal to 1. So if you have empty set, there are not much of bijections from it to itself. There is just one basically, which means not do anything. But that's just, you can think of it just as a convention. Okay, so these are these permutations. In particular, you can see from here that we'll see later that these permutations are nicely divided into two types. So these guys will be called even, and these guys will be called, this guys will be called odd, and the rest will be called even. And we'll talk later about what that means, even, but it has to do with the number of crossings here. So here the number of crossings is 2, and here the number of crossings is 1, here it's 3, here it's 1, and here it's 0. And so here it's even and here it's odd, so all permutations can be divided into two classes. But that will appear later. Okay, so next, let's see what structure does a set of permutations have. So what can you do with permutations? And the main observation is you can combine them. So if you permute stuff, then you can permute it again and again and again, and you can just keep combining these ways to permute something. And that's what's called a product of permutations.